Today, in this session, we are going to explore one of the most classic and elegant topics, that is the toy problems. So, are these problems for children? But when we talk about AI, these are powerful tools that helps build, test, and understand intelligent problem solving systems. So, by the end of this session, you will understand exactly what toy problems are, why are they important in AI research, and we will walk through a lot of toy problems. So, to begin in this session, we will discuss about the monkey and the banana problem. So, this is the one that laid the foundation for AI. Okay, right. So, toy problems. So, what actually it means? So, in the field of AI, we often need environments where we can test, refine, and validate our algorithms safely and efficiently. So that is where this toy problems actually comes in. So you can see in this slide there is a difference between toy problem and the real world problems. But when you take the toy problems at its core, it is defined for a specific purpose. So it is used to illustrate or exercise various problem solving methods. Okay. So what makes it special is that it can be given a concise, exact description. That means we can define it completely, we can reason about it completely, and we can program a computer to solve it completely. So when you talk about the real world problems, so these are problems whose solution people actually care about. So think about the real world problems like scheduling the airlines, diagnosing the disease, navigating a self driving car. So these problems tend not to have a single agreed upon description. So actually they are very complex, messy, and there are a lot of ambiguity and uncertainties involved. So the key insight here is that toy problems serve as a training ground for real world AI. So we develop and validate our algorithms on toy problems, and then we scale those techniques to real world applications. Now we will discuss upon the characteristics of toy problems because understanding this will help you to recognize them wherever you encounter them in the AI work. Now the first characteristics is toy problems are not real world problems. They are deliberately simplified and generated specifically to test problem solving approaches. It's often used for fun or educational purposes. Secondly, these problems are played on a board or paper. You can imagine chess, tic-tac-toe problem, Sudoku. So the environment is physical, bounded, and visible. And you can see the problem environment is always controlled. You don't have any surprises. There are no unexpected factors. There is no ambiguity, uncertainty. Fourth, problem formulation is possible because the boundary conditions and constraints are known in advance. You know what are the moves that are legal, what the goals look like, and what is the starting point. For example, if you take chess, you know, right? What are the positions of the coin, when the goal is achieved. then these toy problems can be converted to computer program. So if you cannot formalize it, then you cannot program. So these problems include tic-tac-toe, 8%, etc. These are games, but when you talk about AI, they are perfect for laboratories. So they are used as a problem-solving venture to a space to experiment with search algorithms, heuristics, planning methods, and intelligent agents. But this seems to be simple, but when you look into it, they are really hard, computationally hard. So in this session, we will start a discussion with the monkey and the bananas problem. So it might be like very simple, but this simple problem contains all fundamental ingredients that an planning system needs to work with. This problem has been used in AI classrooms for decades. So once you understand it, you will use its fingerprints in almost every AI planning systems. So now this monkey and banana problem was first introduced in 1960. Its primary purpose was to demonstrate how AI planning agent works, specifically how an intelligent system can define and find a path achieved. Okay. It illustrates two important things here. One is defining the goal, and another one is finding the path. So defining a goal means what does success actually look like? Finding a path means what sequence of actions gets us there. So the problem involves preconditions and effects. Every action has a precondition. Things must be true before an action can be performed. And every action has an effect because it changes the state of the world. So this is the foundation of formal planning languages. This problem directly inspired by STRIPS, the Stanford Research Institute problem solver, which was developed in 1971. STRIPS became one of the most influential AI systems ever built, and it is the ancestor of modern AI planning languages like PDDL that are used today. And after so many years, still this has been used in teaching because it clearly captures the essence of planning, search, and logic. Now we will look at the description of the problem. So you can see there will be a monkey. There is a monkey in the room. You can see the bananas are hanging from the ceiling and it is out of reach from the monkey. The monkey cannot jump up and grab it from the ground. So there will be a box somewhere on the floor in the room. The monkey is strong enough to push this box around and it can climb over the box and grab the bananas. But it should be positioned correctly. So if the monkey pushes the box under the bananas, climb on top of the box, and if it is able to reach it or grab the bananas, all these are possible only if the position of the box is correct. So the question here is, what are the sequence of actions should the monkey take to get the bananas? So this is what the AI planning agent must actually figure out. The agent starts in some initial state, has a set of possible states, actions, and needs to find the sequence of actions, a plan that leads from the initial state to the goal state. So this problem is one of the oldest example to teach about the state space search. Okay, right. Now you can imagine from your room that there are bananas hanging and a monkey is there trying to push the box. Okay, so now we'll discuss about the states and actions. So how to formalize it? We need to formalize it. For that we need states and actions. So our initial state is the monkey is on the ground with empty hands and the bananas are suspended from the ceiling. The goal state is the monkey is eating the banana. That is a success we are aiming for. So the available actions for the monkey are it can climb the box, it can get off the box, vertical movement onto or off the box. There will be a stick, it can grab the stick, it can drop the stick. So obviously for grabbing it has to pick up or put down the stick. For waving the stick, we use the stick to knock the bananas from the ceiling. It uses. It can grab or drop the banana, that is take or release the banana. Or it can eat the banana. This is the goal stage. Notice that something very important here. Each action has a precondition. You cannot grab the banana unless the banana is within reach. You cannot wave the stick unless you have the stick. The monkey cannot be on the box unless the box is positioned correctly. So these preconditions are what makes the AI planning problem not just a simple sequence of steps. So what if the monkey tries to grab the banana while still standing on the ground? Think of the preconditions. Is there any precondition? Now we will talk about the state space. So what is a state space? State space is a set of all possible configuration the problem can be in. So there are four variables: the monkey location, the box location. Monkey is monkey is on the box or whether the monkey has the banana. So when we talk about the monkey location, where is the monkey? It can be at any of the position A, B or C. Box location. Where is the box? It can be positioned again at A, B or C. Whether monkey is on the box, it can be on the box or off the box. So S or no. Whether monkey is having the banana, S or no. So these are the possibilities. So all of these variables together define a single state node in the search space. Each unique combination of values is a different state. Now, let us calculate the total number of possible states. So when we talk about the monkey location, it has three possible positions. Either it can be in A, B or C. So there are three options. If we talk about the box location, again it has three positions. It gives us three options. It can be in either A, B or C. Whether when we talk about whether the monkey is on top of the box, yes or no, gives us two options, yes or no. So whether the monkey is having the banana, again there are two options, yes or no. So when you calculate the total number of states, there are 36 possible states. Point here is, not all 36 states are actually reachable. So consider the state where the monkey is on top of the box Now, where the monkey is on the box, but both are at different locations. It is physically impossible. The monkey cannot be on the box if it is somewhere else. So the effective reachable state is much smaller than the calculated statistics. So when we see that, when the search space becomes smaller, means your searching becomes faster and more efficient. So when formulating problems, think carefully which states are actually valid and reachable. Good problem formulation can dramatically reduce the computational cost. Now, let us look at this tree visualization. Okay. Now, the agent systematically explores the search space, the state space, looking for a path from the initial state to the goal state. When we draw out the search tree of this problem, there are three main branches you can see. The left branch, if you come here, monkey on the ground and empty hands. This is the start state. Okay. The monkey can climb on top of the box. The monkey climbs on the box with empty hand. So realizes it cannot reach the banana because it has nothing to grab them with. So it gets off the box and returns to the ground. No progress was made. Okay. So it's a dead end. The monkey grabs the stick but then drops the stick here. If you come here on the ground, it grabs the stick and drops the stick. Again, there is no progress. It's a dead end. If you take this right branch, starting from grabbing the stick, so monkey with the stick on the ground. Then all the way it goes down to the sequence of steps to reach the goal, that is the banana, eating the banana. So it's on the ground with the sticks. Then it climbs on top of the box. Now monkey on the box holding the stick. Now it's trying to wave the stick, so banana falls on the ground. Monkey still on the box. Now it is getting off the box, so monkey on the ground. So banana on the floor and it still has the stick. Now the monkey drops the stick, it's on the ground with empty hands. So bananas are very nearby. Now it's taking grabbing the banana. So monkey on the ground holding the banana. Finally the goal state eating the banana. Monkey is on the ground and eating the banana. So this visualization shows up something very important. Not every path leads to the goal. An intelligent agent must explore the dead ends quickly, backtrack and try the alternative paths. Now here it came to a dead end, it backtracked, again it came to a dead end, it backtracked, then it found out the. So the algorithms like DFS, BFS and A star does the same. Okay. So we will look at already we looked at the correct path, right? So the correct path was already discussed. There are about 7 steps, right? Monkey on the ground with empty hands, grabbing the stick, climbing the box, waving the stick, getting off the box, dropping the stick, and then eating the banana. So this is the optimal plan. So each step satisfies the preconditions for the next step. Each step changes the state of the world so that it goes to the goal state or the next possible state. So we discussed about 3 branches. Left branch which led to the dead end path, that is climb chair with empty hands, get off the chair, back to the ground. And middle branch, that was dead end dead end path, grab stick, drop stick, go back to the ground. This right branch was essentially the solution. This chain of cause and effect in this previous slide, precondition satisfied, action is taken, and a new state is created. So from here, this new state is created. So this is a fundamental mechanism of all AI planning systems. Okay, right? So this is what I've given in complete. Together I have given. Same thing, what I discussed. So the final solution path is given for you here. So monkey was on the ground with empty hands, grabbing the stick. It will climb the box, wave the sticks, get off the box, drop the stick. Monkey on the ground with empty hands, and finally it is eating the bananas. Okay. So this is where the final solution comes out with proper planning. I hope the problem is clear. So these are the references from Stuart Russell and Peter Norvig, Parag Kulkarni and Elaine Rich. Thank you.